Have you ever just wondered what would happen if you fired a bullet from space, like straight down at Earth? It sounds like something right out of a sci-fi movie, doesn't it? But the answer, well, it's all about pure, mind-bending physics. Let's figure this out.
So, here's the big question we're tackling today. Could a simple, everyday bullet actually survive that insane, fiery plunge through our atmosphere and hit the ground? It's a fantastic what-if scenario, and you know what? The science behind it is absolutely fascinating. Let's dive in.
All right, first things first. Let's really set the stage here. We need to get a clear picture of what we're talking about to really understand the incredible journey this little object is about to take.
Okay, so picture this. A tiny bullet screaming towards Earth at thousands of miles per hour. As it starts to hit the very top of the atmosphere, it begins to glow, and then, whoosh, it erupts into this brilliant fiery streak. But what's actually causing that incredible heat? I'll bet the answer is not what you think it is. Now let's move on, because we need to bust one of the most common myths about objects re-entering the atmosphere. See, most of us have this built-in idea about what causes things to burn up, but it turns out that idea is mostly wrong. So just take a second and think about it. When you see a meteor streaking across the night sky, or you see footage of a space capsule coming back home, what do you think is creating all that fire and light? Is it just the air rubbing against the object, but like really, really fast? The common myth, the thing we all tend to think, is that it's all about friction. You know, like when you rub your hands together to warm them up. But the scientific reality? Oh, it is so much more dramatic. It's not friction, it is catastrophic air compression. The object is moving so insanely fast that the air literally cannot get out of the way, and that compression is what generates the mind-boggling heat. So let's talk about this wall of air. How on Earth does just slamming into our atmosphere at orbital speeds create temperatures that can be hotter than the surface of some stars? Let's break down the science. It all comes down to one simple concept: kinetic energy. Our bullet, traveling in orbit, is moving at a staggering 17,000 miles per hour. That's not just fast, it's an incredible amount of stored energy. So when that bullet suddenly hits the brakes by slamming into our atmosphere, where does all that energy go? Okay, here's how it plays out. The object hits the atmosphere so hard and so fast that the air molecules just can't escape. They get squeezed together in front of it, creating this super dense shock wave. And all that kinetic energy, all that energy of motion, has to go somewhere, so it gets dumped right into that tiny pocket of trapped air, converting into an unbelievable amount of pure heat. So how hot are we talking here? Try up to 5,000 degrees Fahrenheit. That is hotter than the melting point of steel, hotter than titanium, hotter than pretty much any metal you can name. Our atmosphere effectively becomes a furnace, and our poor bullet is flying right into the heart of it. Right, so if re-entry is that brutal, how does anything survive it? How do we get astronauts back to Earth safely? The answer, my friends, is some truly brilliant engineering. Understanding this isn't just a fun thought experiment, it's literally the key to all human spaceflight. Let's take a look. The answer is a piece of technology you've definitely heard of, the heat shield. This is not just a simple piece of metal. It is a highly advanced, purpose-built system designed specifically to manage and deflect that insane 5,000-degree heat away from the precious cargo inside. And there are a couple of really clever ways to do it. The Apollo capsules use something called an ablative shield, which literally burned away, layer by layer, carrying the heat away with it. Super effective, but a one-time use. Then you have the space shuttle, which used those famous black tiles that could absorb the heat and then radiate it back out into space, making them reusable. Two totally different approaches to solving the same deadly problem. Okay, we have all the pieces of the puzzle now. We understand the problem, that extreme heat from air compression, and we've seen the engineering solution. So let's bring it all back together and give the final verdict on our little space bullet. So let's look at our bullet. Does it have a protective heat shield? Nope. Is it big enough to absorb any heat? Not at all. It's tiny, and it's made of lead and copper, metals with really low melting points. It is basically the worst possible design for surviving re-entry. It's about to hit that 5,000-degree wall of superheated air completely naked. And that leads us to our definitive answer. The bullet wouldn't just burn up, it would be utterly obliterated. In a matter of seconds, it would flash from a solid to a liquid to a gas, leaving nothing behind but a faint, glowing trail of vaporized metal high up in the atmosphere. It would never, ever come close to hitting the ground. So a bullet doesn't stand a chance. But that brings up a really interesting new question, doesn't it? If a bullet vaporizes, how can a random rock from space, a meteor, sometimes make it all the way through that same furnace and actually strike the ground? Something to think about.